Good morning, OCP Global Summit 2020. I'm Michael Smolin from Samsung's Data Center SSD Product Group. This presentation is titled Rethinking SSD Storage at Scale. Solid-state drives are a critical technology in today's cloud data centers. And over the years, SSD technology has advanced tremendously in terms of capacity and performance. So why do we need to rethink anything? There are three reasons. First, to increase efficiency by addressing issues intrinsic to NAND-based SSDs. Second, to better address scalability of SSD behind huge data sets and dense nodes. And finally, to maintain flexibility so that today's systems can grow to support future needs of data. Today's SSDs offer millions of IOPS and tens of terabytes of capacity. But SSDs still suffer from efficiency problems related to their fundamental nature. Traditional SSDs are dumb block devices, which present an array of small logical blocks of servers while hiding the larger erase blocks, which are the native granularity of NAND flash memory. The translation from logical blocks to physical blocks is done by a flash translation layer. In steady state, old pages have to be erased to make room for new writes. And useful data sitting on erasable pages must be copied over to newly allocated pages. This copying leads to write amplification, which decreases SSD life. At scale, SSD background operations, such as garbage collection, can create unpredictable latency spikes, which contribute to long-tail latencies, which in turn hold up completion of data-intensive queries. Today's cloud scale is in the millions of servers. User-generated content continues to pour in. YouTube receives more than 500 hours of video every minute. And Facebook receives 350 million photos every day. And zettabytes of machine-generated content is expected to come. To house this data explosion cost-effectively, new data center facilities sized in the millions of square feet are not uncommon. For example, Facebook recently announced plans to expand their 900,000 square foot facility in New Albany, Ohio. After the expansion, the complex will total 2.5 million square feet. And it's not just the buildings that have scale. Today's data lakes can often be 10 exabytes or more. Executing a query against such a large data lake is fraught with issues. For one thing, servers often sprawl out across the data center in order to meet performance and productivity requirements. Since the data set needs to move to the CPU for filtering, most of the I/O operations will be wasted in a typical high selectivity query. And in the process, caches will be polluted with data slag. Finally, flexibility is critical to ensure today's systems can benefit from tomorrow's innovations. As we've seen from extensive roadmap delays in 10 nanometer CPU platforms, process technology-led advances are becoming less certain. Luckily, the creativity of system architects and algorithm designers continue to provide innovation in what John Hennessy and David Patterson are calling a golden age for computer architecture. A variety of areas are benefiting from new algorithms and architecture. For example, for data analytics, columnar file formats such as Parquet are replacing simple row-based formats such as CSV and JSON. And in video, ever more advanced codecs are keeping storage and transmission requirements from exploding as resolution and volume continue to grow. While fixed function ASICs can benefit from these advances, the ideal solution combines the parallelism and speed of hardware with the programmability of software. So why rethink SSD storage at scale? For efficiency of operations, for scalability to 10 plus exabyte data lakes in multi-million square foot data, and flexibility to adapt new algorithms and architectures, which are increasingly the source of computing innovation. Now, to talk about how we can rethink SSD storage at scale, I'd like to welcome Pankaj Mehra, VP of Storage Pathfinding at Samsung Device Solutions America.
Thank you, Michael. So to double click on some of the points that Michael raised at the end of his talk, let's dive into the details of what it is like to handle data at scale. First, like Michael was saying, that at that volume of data, such as the exabytes and data lakes he described, the need for scaling processing power and data bandwidth with the amount of data is paramount. Without it, there are bottlenecks in the system related to data funnels. Second, with the large number of objects, such as might be found in an image processing or image search system, the sheer metadata inefficiency and the need to update it frequently and having it update in a decoupled way from the objects themselves leads to wasted resources, such as wasted endurance on storage and higher latency and lower throughput. Finally, to deal with the very large number of virtual machines being launched every second, and to deal with the data that those virtual machines then need to use, we need efficient and independent scaling of compute and storage. The idea in place for that is disaggregation. But today's disaggregation for storage is extremely inefficient because it terminates unnecessary protocols in front of the SSDs instead of at the SSDs. So these inefficiencies then result from the bottlenecks and look like inability to deliver both performance and scale at the same time. Or if you're using flash for performance, then not being able to keep it long enough because you're writing it over and over more times than necessary. Or you're pulling data into the CPUs near where it wastes L2 to memory bandwidth, causes overhead of IO handling, and even virtualizing storage and virtualizing networking, CPU inefficiency, because instead of resources going to the virtual machines, they end up going to the IO virtualization itself. Okay, so to see what ideas are in place to deal with some of these issues, we are going to look at how the modern SSDs can help. On to the right, you know that people have already been looking at some of these issues, such as companies like Vertensys and others look at virtualization offload. Since hard disk drive days, we have looked at SMR, DB, and active disks, and storage networking convergence is as old as Fiber Channel. And even the idea of offloading the bottom half of the file system to closer to storage dates back to the 90s from Garth Gibson of CMU. The problem with these ideas is that they have been implemented at system and software level, where we are having to put like an x86 tax on storage, so that we are having to put almost 2 sockets of Intel on 4 or 8 SSDs in a chassis. And then when we need to deal with more data, we have to build new nodes with more CPUs, whether they are storage nodes or compute nodes. So the new trend in storage is that these ideas are now coming to live in the SSD, where no x86 tax is necessary. So let's examine left to right in this slide. For example, for disaggregated storage, the new Ethernet attached SSDs will allow you to terminate the NVMe fabric protocol not in front of the SSDs like at Mellanox Bluefield or Broadcom Stingray, but rather at the SSD itself. In case of computational storage, like Michael was saying, the idea we need is speed and parallelism of hardware with the programmability of software. Well, that idea is called FPGA in technical speak. So the new SSDs like Smart SSD will pack an FPGA in every SSD. And likewise, the KV SSD, which is actually our most advanced product in workload optimized portfolio, the handling of complex objects rather than splitting those objects into fixed size blocks as old traditional storage used to require. The new KV SSD deals with application objects at their size and their quantity. This allows storage and alignment to happen much more efficiently, preventing unnecessary write amplification, which results in lower latency and higher throughput. So the reason we are revisiting these ideas in 2020 is because these 25-year-old ideas that started with Fiber Channel, Active Disk, and OSD in the 90s are now being exercised by the SSD instead of by a system of computer and software in front of the SSDs. So let's look at the Smart SSD first. Like I said, the Smart SSD packs a Xilinx FPGA in front of an enterprise-grade controller over a high bandwidth data connection that is private to the device. The private connection means that as you add more data bandwidth, and you add more processing capability because each drive brings an FPGA. To understand why that would benefit some of the workloads that Michael talked about, let's look at the middle pane. In red is shown what happens in the traditional architecture when compute is happening in front of storage. After 4 to 8 SSDs, we have seen this in data warehousing system and media processing systems. After 4 to 8 SSDs, the performance starts to flatten. This is called roof lining, and it's a bad thing. What we would like to do is we would like to keep scaling that performance right past that roof line, and even preferably do it at a better slope. What that means is that as you add more and more data to the system, your performance keeps up with that data and keeps up even better than it does with traditional SSDs. The reason is this internal bandwidth can be better and greater than external bandwidth that we see in SSDs today. To see the benefit in practice, look at the 3 panes on the right, starting with the top. Here we show, like Michael was saying, big data lakes are built with Parquet data, but data scientists want to query it using traditional SQL-like mechanisms, not using batch MapReduce. So in the traditional way, you would have transferred that data as shown in the red here. You would have then decompressed and filtered it on the host CPU, and then applied join and aggregation processing. With the Smart SSD, you can push that decompression and filtering to the SSD itself, resulting in much reduced data, as shown in green, being transferred back to the host CPU. And then even if you don't optimize that join or aggregation, you still end up with 2 to 3 times faster query. Below that pane is shown what happens in media handling. In red, you see the CPU utilization of a transcoding job using FFmpeg as you use video data stored on SSD. After 3 SSD, you can see that the CPU is fully packed. But if you use Smart SSDs, 3 SSDs not only do the work of two full sockets of Xeon 2630, but do so at a much lower CPU utilization because they have offloaded it. As a result, now you can keep adding more and more media to a single server and do sometimes 10 times the work of a normal 2-socket server when you are using Smart SSDs instead of using traditional SSDs. Finally, at the bottom is shown a decompression task. This is a very routine storage management task. Here we built a server in our lab with 24 Smart SSDs, all decompressing in parallel. In green, you can see the bandwidth of decompressed data. And in blue, you can see the bandwidth of the compressed data that is being pulled into the FPGA. You can see performance scaling linearly. This is unprecedented. Moving forward, not only we want to make these devices available to our customers, and below you can see Alibaba and Zoom have already gone public that they're working with us. These devices that we have today have 4 terabytes of flash. They expose a Gen 3x4 external connection and pack 500,000 LUTs worth of FPGA acceleration. Moving forward, we are working with our customers, such as yourself, on requirements to integrate deeper and more variety of accelerators to offer even richer and standard interfaces from these Smart SSDs, and to deliver these devices not just in the U.2 form factor, but the form factors additional ones that you want in your data centers, and to cover even more workloads for acceleration so that you can deploy these Smart SSDs everywhere you deploy SSDs. Next, let us look at storage disaggregation and Ethernet attached SSDs. In today's situation, the problem of building JBARs or just a bunch of flash is not very difficult, because the SSD is only doing about 3 gigabytes a second, and the Ethernet in front of the SSDs can keep up. As we move forward and SSDs deliver more and more bandwidth, a gap starts to form between what the SSDs can do at 150 gigabytes a second and what the front end can keep up in terms of 75 gigabytes a second. To examine why there is a bottleneck, you have to understand what is in front of those SSDs. Let's look at the next slide. In the way we build just a bunch of flash today, we terminate the NVMe over fabric disaggregation protocol in Mellanox Bluefield or Broadcom Stingray in front of the SSDs. The limited memory bandwidth and the limited processing capability of these systems means you cannot have very many SSDs behind each of these front ends. Moving forward, as the Ethernet attached SSD terminates the NVMe over fabric protocol directly, you not only end up with fewer protocol terminations, which results in fewer pipeline bubbles, lower latency, and higher throughput, but now you can have many more SSDs in every chassis, which minimizes data center, physical management, complexity, as well as cost. In this, same as with Smart SSD, we have a current prototype that is in U.2 form factor that we are working with various SmartNIC and other partners in the industry to test. Our goal is to deliver product quality Ethernet attached SSDs in about a 2-year timeframe. And we are working with our customers on areas such as security division of labor between host, front end, and device, physical management of these devices, and working with various numbers of initiators, high or low, and working on data center fabric congestion control protocols. So please talk to us about your requirements. Finally, let me talk about object storage at scale. So if you look at high performance object storage today with block SSDs, which is the product that you would find today in most data centers, the burden of aligning those objects to the storage boundaries is left to the CPU and DRAM, which does this so inefficiently that wasted endurance translates into high write amplification factors at application and device level. Off to the right, you see if the device can understand application level objects and manage some of the metadata keys that are associated with that object, then the CPU ends up with a much lighter task because it is dealing with objects that are aligned with memory representation. Transfers to memory and from storage are both much more efficient, which benefit is then illustrated in the middle. So just as in case of Smart SSD, on the x-axis is shown how many SSDs you would have in a single server behind, say, 2 sockets of x86. And on the blue line, you see what would happen if you use KV SSD versus the gray line shows what would happen with traditional SSDs. So you can see that the higher slope scaling of KV SSD clearly illustrates that benefit of the KV SSD technology. It's shown even better on the next slide, where we have looked at the RocksDB NoSQL database and typical benchmark queries performing on that. And we show 4 dimensions of benefit here. On the top left, we show 60% improvement in latency. On the right, we show not only better throughput quality, less jitter as well. And then in the bottom, we show to the left, much reduced write application factor, which means your flash memory lasts long, which results in 11x CapEx benefit for data center customers. So moving forward, we are continuing to advance the KV SSD firmware. We are tuning it for more workloads, such as AI ML workloads these days. And we are working with our customers on integrating this better in the stack, such as Cassandra and ROCks. Also working with you on continued improvement in standard interfaces to KV SSD, delivering the device in newer form factors, and tuning it to newer workloads. So we are in advanced stages of partner testing here and very much welcome your engagement with us. So let's summarize the benefits of the technologies I've talked about today, as well as zoned namespaces, which is being talked about by Samsung in other talks at this meeting. As you can see, Smart SSD with its very versatile acceleration platform has the most benefits in terms of application awareness, acceleration, and keeping that data out of the CPU and saving some of that precious L2 memory bandwidth as well. Ethernet SSD is specifically meant for storage services in a disaggregated environment where it reduces the number of protocol terminations and stack translations, resulting in being able to hold more SSDs per chassis for better TCO. Finally, KV SSD, just like Smart SSD, is very application oriented. Its savings mainly come in terms of improved write endurance for variable shaped objects, such as media objects and compressed data objects. And it really excels in metadata optimization at the device, therefore resulting in fewer stacks translations related to object conversion and metadata. And also permits you, as we showed with the RocksDB benchmark, to hold more SSDs per chassis for bigger data at lower cost. So in the future, what we hope to do is, instead of offering you A or B or C, we realize your workloads may require us to combine these benefits. So we are working with our customers from my storage pathfinding team to offer them a choice of host interface, such as both PCI and Ethernet options, choice of address translation layers, such as both block and key value, along with ZNS for QoS purposes. And then finally, choice of accelerator, of which we have FPGA first. So you can either have that accelerator if you want to spend the power or not have it. These are then shown on the right with how various workloads such as data lakes and large media stores, as well as dense compute environments and future integrated backend as a service workloads such as Lambda can benefit from our work. So let me turn it over back to Michael to tell you where you can go to learn more.
Thank you, Pankaj. There's more to learn about the different technologies that Samsung is working on to rethink SSD storage at scale. As Pankaj mentioned, we have another session on zone namespaces with Javier Gonzalez. We also have a virtual booth here at the show. We have experts in different topics ready to show you our demos of products and technologies and answer your questions in more detail. You can also visit our website, which is events.samsungatfirst.com/OCP, where you'll see an overview of our different products and technologies. Okay, we are now live in the Q&A portion. Pankaj, we have our first question from the audience regarding Ethernet attached SSDs. Does it support level 2 or level 3 switching? And if it supports level 3, how could we configure the IP address?
So first of all, thank you for attending and thank you for the question. Thanks, Michael. The L2 and L3 are both supported. The device works with switches in front. So higher than L3 functionality is going to be inside the SSD as opposed to be outside, although management may vary. As far as configuration of IP address, that can be done with either IPv6 or NDP protocols. Okay. Yeah, Michael, go ahead.
Okay. We have another question from the audience about Smart SSD. The question is, what is the power consumption difference we are seeing with Smart SSD running at max load versus a traditional SSD running at max load?
This is a good question. You know, I think the questioner knows that the modern SSD is a power limited device, especially in an all-write workload. And when you add the FPGA, and in the beginning, these early devices are not deeply integrated. So power under a full write workload, you actually have to decide whether to throttle back the SSD portion or the FPGA portion. We are also conducting some measurements in more reasonable analytics-oriented workloads, which are not 100% right, but rather read-intensive workload with the FPGA processing the data coming out of the SSD. At least some initial observations on the analytics workload with BigStream are showing that even without the power management and temperature-based throttling algorithms running, we are under the 25-watt envelope of U.2. And we also have some tests together with Xilinx on controlling either the FPGA through our voltage and frequency scaling approach, or controlling the SSD where we slow down the writes. And working with specific hyperscale customers, which we are working with several of them right now, you can take part in specifying the policy that the smart SSD will implement in the power saturated situation. Thankfully, in many of the workloads that I described, where the delivery of the smart SSD benefit is read oriented, it is not such a critical issue.
Great. And we have a third question from the audience. The question is, how do you see these technologies playing out?
So, as I said on my last slide, that we see that, the big forces in the industry where data is growing unprecedented, for example, conventional workloads such as data lakes and media stores, but new emerging workloads in gaming and AI, they are pushing the envelope and requiring more than one of these features to be in the same SSD product. At present, ZNS and these technologies are becoming normal feature of SSDs. The cost and power envelopes of the other technologies and the fact that Ethernet SSD requires you to go to a non-PCI interface means you'll be choosing these in combination. So like standard product work, we are working with our customers to see which requirements hang together. And moving forward, you can expect that we will do small, medium, large, with some minimal smart and some maximal smart in SSDs as an option. We could also give you a choice of interface like PCI versus Ethernet, and a choice of firmware such as KV firmware or non-KV firmware. We are still working out the details, so there is no roadmap commitment to be implied by my comments. But we now have these technologies in hand in isolation, and now we are starting to play with them in combination. So, for example, eSmart, we consider very likely, for example.
Great. Well, we are out of time for this session and out of audience questions. So I'd like to thank everyone again for attending the session. If you have additional questions and would like to talk with our experts, please stop by the Samsung Virtual Expo booth and you can talk to us there. Thanks again, everyone.
Thank you.